All right, so we'll just do a quick Chapter 8 review before the test today. One of the first topics that we had new to us was complex roots, or complex numbers. So we found out that sometimes when we were solving a quadratic, for example, that we get that square root of a negative. And remember, we have what's called the discriminant, which is underneath the square root, the b squared minus 4ac. If the discriminant is negative, then we get non-real or complex solutions. Now we can add i's together, we can subtract i's like normally, kind of the algebra rules if it were an x. We can multiply i's, and the big thing that we got from that is the square root of -1 was I. So if I, for example, if I do I squared, that equals -1. So by squaring i's, we get back to real numbers, and that was the real advantage. Sometimes we may have to divide by i's, but we're not going to leave it in this form. Why I picked dividing complex numbers is it brings in that idea of the conjugate as well. That is important for later in the unit when we're starting to find roots. So to divide two imaginary numbers, what I just do is I multiply the top and bottom by the denominator's conjugate. Now remember, by multiplying by a complex number's conjugate, you get all real numbers. So again, I'm multiplying by 1 just because it's the same on top and bottom. But on the bottom, I'm actually going to get real numbers for that. So I'll do the top first. You can use our generic rectangle as if it were just a normal like quadratic. Those were x's. Then I get 1 minus 5i. So it looks like I'd get a 5 in this box, a -4i, -25i, and then a positive 20i squared. But that's the big thing here on top. You're going to get some number in terms of I. We do always want to write complex numbers with the real portion first and then the imaginary second, so we call it a plus bi form. So this 20i squared, since we know I squared is -1, this is actually just -20. So if I have -20 and a 5, that's a -15. And then minus 29i. And just to show it, the actual multiplication of the conjugates, there is a fast way to multiply these. I'll show that afterwards. 1 minus 5i. So I get a 1, I get my minus 5i, I get my positive 5i, that's why they, oops, sorry. So they cancel, and then you get this -25i squared. Well, again, these cancel, and this is a real number. That's a positive 25. Because I have -25 times -1. So really on the bottom, all I have is 26. So the whole goal, or what you can do, is by multiplying the conjugates, it's really just if this was a plus b, this was a minus b, it becomes a squared minus b squared. But in this case, since the I is negative, that we add those two numbers together, so it becomes a 26. Like I said, we should write it in a plus bi form, so we just separate those two. So I get -15 over 26 minus 29 over 26i, and then I can simplify any fractions if they show up. Okay, so that's how to divide by i's, but again, knowing all the operations is important. Moving on, we talked about the number of roots. We introduced higher degree polynomials. So a degree 2 was a quadratic. Degree 3, we named it cubic. It got to an x to the third. And then degree 4 was quartic. But all of them have like an x squared in front, an x cubed in front, and an x to the fourth in front. They might have coefficients, but what we wanted to look at is we want to be able to make the equation for this graph. Just like we would a quadratic or a cubic, this one actually ends up being a quartic with that W shape. But what we want to be able to do is if I know a 0, like on the graph I know an x-intercept, then I know a factor. So for example, this goes through -4. I'm going to have a factor in the equation somewhere of x plus 4. I have an x plus 2 factor because it goes through at -2. Then I have this x minus 3 factor because I know it hits 3. But this is a big key characteristic. This idea right here is something that we're going to look at as well, that it bounces on the x-axis. If it bounces, it has a double root or repeated root. It means there's another factor of x minus 3. And that's how we get the degree up to 4. So that's all good and dandy, but don't stop there. A lot of times we kind of just say, well, that's it. Remember, these can have some sort of a stretch factor, or they can be, the peaks and valleys might be a little bit higher or lower. So we have to find an a value, just like we did with quadratics way back when we were doing like the field goal kicks and the soccer ball kicks. We wanted to know how stretched out it was. So all I have to do is pick a point. A lot of times we'll give you the coordinate, and we want to pick an exact one. We'll say this goes through 0, 3, but that means the x is 0 and the y is 3. So I go 3, and plug it in 0 isn't too bad. So I get 3 equals, I get 4 times 2 times 9. So I get 36, 72. Okay. I divide that by 72 to get a. So instead, I want to simplify that. 24, I think. 124. I think that's into that, right? Yeah, 12. Perfect. So this would be my final equation. 1/24 x plus 4x plus 2x minus 3 squared. Similar to that, we're not going to make the equation of this, but we may ask how many roots a polynomial has, and it's all based on these x-intercepts. So it may have real roots, it may have complex roots, and I'll show you what a complex, when a situation where I may have a complex root which isn't necessarily shown on the graph. So again, I would say this bounce right here, that's going to be my double root. So double root bounces on that x-axis. It's not like a dip anywhere. It has to hit the x-axis. Now, right here, it does go through the x-axis, but it does what we call a little shimmy. So if you have that shimmy, it has a triple root. So if this is at, I don't think it is, but 1, 2, 3, like I would have x minus 3 cubed. I think the x-axis or intercept is a little, actually it may be, no, it probably is. And then a single root, like if you just have a factor, is when it just goes straight through. It doesn't do a shimmy. And we have like an example of that right here. So writing the equation for a polynomial that does have imaginary roots. For example, I want to go back to this one. I got this question a lot, like, hey, I have a cubic, but all I have is one root. So it may ask, okay, there's one real root, but if it's going to have an x cubed, it has to have 3 roots. A quadratic has 2 roots, whether it be both imaginary or both real. If it's a cubic, it's got to have 3 roots. If it's a quartic, an x to the 4th, it has to have four roots. Now that you know about imaginary numbers, so that's kind of the whole goal of chapter 8 here, is that it's a cubic, so I have one real root, but it's got to get an x to the 3rd, so it's going to have 2 imaginary or complex roots. And the thing about imaginary roots is they always have 2. They have a pair. There's never going to be one complex root. So if I look at this one, it says write the equation for a polynomial with roots at x equals 2, and then x equaling 1 plus 3i. So the thing about that's kind of tricky here is you can't just make a one root of 1 plus 3i. There has to be another one, which is that idea of the conjugate. I'm going to have another root at x equals 1 minus 3i. So I wanted to show this as well, just because we've been finding in the homework, finding the equations when we give you non-real roots. But we do it similarly, it just requires a little bit more work. But if I know the answer is going to be 1 plus 3i, I'm going to do the factor the same way. X minus, since it's a positive number, I'll go 1 plus 3i in parentheses, and then x minus 1 minus 3i. Now, I'm going to show that really you don't have to put these parentheses. You can maybe skip a step if you realize this and watch this, but eventually you get x minus 1 minus 3i. Well, you can just do minus this one then, and then x minus 1 plus 3i. So it's really just x minus each of these. Just kind of flip-flops, but wanted to show all the algebra. So then I have to actually multiply these together and distribute, but something pretty cool happens. So I'm going to go to my generic rectangle. It's going to be a little bit bigger because I have three terms. I have x, I have a negative 1, and I have a negative 3i. And then here I have an x, I have a negative 1, I have a positive 3i. So just go through, multiply 9 terms here. So you get an x squared, you get a negative x, and you get a 3xi. Here I get a negative x, I get a positive 1, I get a negative 3i, get a negative 3xi, I get a 3i, and then I get a negative 9i squared. So that's kind of the nice or cool thing that happens. So you actually have a piece of your quadratic here, all real numbers, but then you always have this 3xi and negative 3xi cancel. You want to show this work, you get negative 3i and a 3i. Then you look at this negative I squared, but I squared is negative 1, so negative 9 times negative 1 is 9. So really the quadratic that would make these roots is x squared. I combine my x's, negative 2x, and then it'd be 1 plus a 9 is plus 10. Which makes me, I believe it's got a y-intercept that's positive, it's opening up, so I don't think it's going to hit the x-axis. And then I have my x minus 2 from this original root here. Now, if they wanted it in standard form, yeah, you'd have to multiply these two out, but that wouldn't be, I don't think, too bad of a task. Just a 2 by 3 generic rectangle, and you can get all of those terms. And to find some of those factors, when we have a full standard form, is kind of working backwards. We learned about Polyduco or long division. I'm probably going to use Polyduco on this one. Just because. So I graphed this in my calculator. That's kind of step one, is make sure you find the intercept on your calculator, or the first root. I know there's a bunch of stuff going on here because it's a cubic, that this goes up here, and it gives me an indication that there's no more real roots. This is the only one. But we can talk about that after the division. So it looks like it goes through negative 3. So if the root is negative 3, we have to be careful that the factor is x plus 3. So that's a mistake that a lot of students make, because they put x minus 3 in your Polyduco. But really what I'm doing is taking this cubic and dividing by x plus 3. So I set up my Polyduco, which is just kind of the reverse generic rectangle. I got to get to x cubed plus x squared plus 2x plus 24 from all of these boxes. So like I said, we're kind of piecing together a generic rectangle to get to that. So I think, okay, well, what times x gets me x cubed? Well, that's x squared. So x squared times x does get me x cubed. But that allows me to get the next box, which x squared times 3 is 3x squared. And this is where sometimes we get stuck a little bit, is, well, I have 3x squared. What do I do from there? I can't get this one. It's all going back to this. The original is that I'm going to add up all these boxes to get to this. So I take a 3x squared, and I'd have to subtract 2x squared to get to that. So then that allows me then to find this top dimension, would be negative 2x, which would then give me a negative 6x here. Same thing. I got to get to a 2x, so I'd have to add 8x, or just add 8, sorry. That should be on the top there. Oh, I'll add 8x. Let's add 8, and then 8 times 3 is 24, so I know it went into there evenly. So really the factored form of this, and be careful how, following directions. If we only ask for the factored form, you don't solve it. You're just asking, okay, here's the factored. The x plus 3 times x squared minus 2x plus 8. There it is. Now, a separate problem, if we ask, find the zeros, that's a totally different question. Now you do the same thing. This is like step 1, but then I have to solve these two factors and set them equal to 0 to know what the zeros are. So one of them is x equals -3. This one I know is not real, so I'm going to use the quadratic formula, where I'd get 2 plus or minus the square root of 4 minus 4 times 1 times 8. I always wanted x equals over 2. If the x equals, it looks like 2 plus or minus, that's a 32. 4 minus 32 is a -28. Some mental math here. 28 is not, to take a 4 out, so it would be x equals, if we took a 4 out, that'd be 7, so we're going to have x equals 2 plus or minus 2 root 7 I all over 2, which we could then simplify. Our final answer would be 1 plus or minus the square root of 7 I. Did a lot of mental math there, so if I made a mistake, sorry, but you're just solving the quadratic, so now I have my 3 zeros. If it finds, tell me all the roots, find all the roots. Some might be imaginary, that's okay. But you gotta, whatever, if it's x to the third, you gotta have 3 roots. Some review topics that I just wanted to go over again was maybe finally given the graph, write the equation for that. So we wanted to go over maps again. So I wanted to find the midline of this one, which is halfway between the max and the min. You have to calculate it. This one's kind of easy because it goes from 3 to -3. So I'm going to have my midline here. The amplitude then is 3. So that's at y equals 0. Make sure you have y equals. Excuse me. Amplitude is 3. Then the period is the distance it takes, or the time it takes to go 1 revolution. Well, in this graph, like it's Ferris wheel, it looks like I got on the bottom of the Ferris wheel, I got to the middle of the Ferris wheel, got to the top of the Ferris wheel, the middle, and then back down. That would be 1 revolution. So that distance right there is 4 pi. So the period is 4 pi, and we're going to get to the equation, but that's not the b value. And then any shift. So what I would do is start with a graph that doesn't have a shift, if you're comfortable enough. For example, it starts at its minimum. You know, this does keep going on forever, but I want to look to see if there's no shift. If I'm looking for no shift, it's on y equals 0. So if it starts at its bottom, the best equation that fits is a negative cosine graph. So I'm going to start with that. Now I'll write other equations here, so you could have a shift. Like if you wanted it to be a positive sine curve, well then you need a coordinate or a point on the graph that's on the midline and goes up first. So like there, color here, that would be a sine curve. Or like my equation would be sine and would have a shift. This, if I wanted to start here, would be a cosine and there would be a shift. Here would be a negative sine. Here would be a negative cosine again. So maybe I'll write a couple of those as well. But going back to our equation, remember the a value, amplitude is right out in front, and your 3 cosine. Now this b value is not 4 pi. Remember the period equals 4 pi over b. Not 4 pi, sorry, 2 pi over b. Thinking ahead here. So again, I'm looking, I have this now. A lot of times we give you the b and you have to calculate the period. Now we give you the period, but a little algebra will help us. So I get 4 pi equals 2 pi over 4 pi, there we go, equals 2 pi over b. I'm going to multiply both sides by b. So I get 4 pi times b equals 2 pi. Then just divide by 4 pi. It says the b value is 1/2. So I put a half here as my b value. There's no shift because it starts right on the bottom, so I just put x, and then my midline is +0. Okay. So thinking about those shifts, the same graph could be written like this. Like if I want to make it a sine curve, well, it would be 3 sine. Amplitude's not going to change. The period's not going to change. It's going to be half, but I'm going to have a shift. If, and we got to think it was from 0, like it was from no shift or no shift, and it moved over to this spot, and everything moved over that. So it started here, it moved to the right pi. I could go x minus pi then inside the parentheses and then plus 0. That would be the graph. These are the same graphs if I graph them in my calculator and up here. It's just one quote unquote is starting somewhere else, or it looks like that midline up, down, and then to here just got shifted over to the right. If you wanted it the positive cosine, well, you shifted it 2 pi to the right. So it would be y equals 3 cosine 1/2 x minus 2 pi plus 0. And then you can do negative cosine was shifted, or negative sine was shifted 3 pi over to the right. So there's infinite graphs that fit that, but we want to be able to find one of these. Then lastly, we talked about to review topics of inequalities. So if I have y is less than x minus 3 squared plus 1, I have a quadratic. This is in vertex form, so I'm going to go over 3 to 3. The vertex is at 3, comma 1. I'm going to graph that. And be careful that it is dashed if it's just less than. And then remember, to solve this type of inequality, it's graphing and shading. There is no number line for this because you have two variables. You have x and y. But what I can check is there is a true region that either it's inside this region or outside the region. To test whether it's inside or outside, just pick a point. I'm going to pick 0, 0, put a little question mark there to say, I wonder if that is actually greater or less than or greater than. So 0 is less than 0 minus 3 squared plus 1. So it's asking, is 0 less than 9 plus 1? Is 0 less than 10? It sure is. So this point is true. So we're going to shade everything on the outside there. Won't get too much closer, but and having a scale is always good to know where this is. And then you may have, another inequality. We had a bunch that overlapped, which isn't too big of a deal. Just write them separately, and then just make sure you know where the true region is, where both are true, and signify that maybe a little darker than the other areas. If you have other questions, that's the same picture I had before. If you have other questions, let me know. We got plenty of review on there as well. So hopefully this worked out.